Thank you. So we're moving from the core, the mantle, and going to the crust, where we have earthquakes. And so I'll talk mostly on the high-frequency part and probabilistic seismic hazard analysis aspects of our work, but I want to give you a little bit of an idea of who SCEC is. So the Southern California Earthquake Center aims to solve issues in earthquake system science. So we care from the dynamics that create the fault rupture, the wave propagation, ground motions, and all that. So it's very holistic. And we use Southern California as our natural laboratory. But it doesn't mean that what we develop is not applicable to other regions. It's just we use that as our main lab. It's a large collaborative center. We have geophysicists, computer scientists, engineers, all those guys working together. And we have a multidisciplinary planning committee that develops a science plan each year. From that, we have a request for proposals, and we fund different projects that follow this mission that we set out. So we support fundamental and applied science, as well as including computer science in there. We have over 1,000 participants. Last year's annual meeting, we had 700 people, more than 700 people showing. We have a set of core institutions and all that, both nationally and internationally. So it's a NSF and USGS funded center, primarily to the tune of about $4.5 million a year. We're a pretty lean organization, given the number of people we support. And we have additional support from Pacific Gas and Electric in California, the Keck Foundation, and other NSF programs for also about $4.5 million a year. So I'm representing here a large group of people. It's not just a single project. Well, you see a lot of those different projects. It's one team. So why do we care? Seismic risk is a big issue in the country, and you would be surprised, not only in California, the central eastern US is also earthquake prone. It's more rare, but they do tend to have big earthquakes. So we care about characterizing that in terms of the 3Ds, dollars, deaths, and downtimes in terms of impacts. And at the basis of everything is the seismic hazard, the ground motions, the faulting, and so on. Then you multiply that by exposure. Is there people in the area that's likely affected by earthquakes? And then what is the vulnerability of the building stock, the infrastructure, bridges, roads, water supply, and so on? You can divide that by resilience. So where we come into play is really in this hazard box here, and we're really working to solve these earthquake system science problems, to characterize seismic hazard risk better. That's what's used as input for design by engineers to basically reduce the vulnerability. So yesterday there was a question about the range of frequencies we cover and relative to buildings and human infrastructure. So we can see here the frequency band from 0.01 hertz to about 100 hertz. And we show different waves in terms of how they propagate through the earth. But for buildings, bridges, critical facilities, and so on, we have a wide range also that we need to cover. So the tanks, water tanks, tall buildings can be low frequencies, 0.1 hertz to 0.2, 0.5, so on. The short buildings and houses are more in the 1 hertz range. And then stiff structures, nuclear power plants, some dams, depending how they're made, and so on, and HPC center, who are very sensitive to high frequencies, mostly because of the content of the structures, all in the higher frequencies. Right now, we do simulations up to 1 hertz in a fully deterministic fashion. We want to increase that. Of course, as we go higher in frequencies, there's a lot of complexities. We need to include nonlinearity, and the scale of the problem becomes big. And it's not that we abandon the low frequencies, we need to add on. So right now at SCEC, most of our simulations go to 1 hertz. We now more routinely do up to 4 hertz. We can do 10 hertz, but then there are issues of how many runs we do and how reliable those results are. So anyways, we want to push to higher frequencies. That's our goal. So ground motion products for engineering. So the motivation is there's limited data sets in terms of recording. So there's magnitude. We don't have a lot of magnitude 8 recorded at 10 kilometers. Well, for sites near San Andreas or Hayward, like the NSERC Center, that might be an issue in the upper 7 and so on. So we don't have also the full bandwidth that can control the design in the recorded data set. So our solution is to simulate earthquakes and their ground motions. And we still need to develop acceptance by the engineering community. So I'm not going to talk much about it today, but one activity that's really important with all the SCEC simulations is validation. You have to be able to go back, and you can create like sophisticated models like there's no tomorrow, and they're beautiful, but do they match the data? And that's really critical. So we're very careful as we increase the physics and all that, we carefully validate. So far, we're getting acceptance. Building code officials are considering CyberShake results for tall buildings in Southern California. The USGS is using CyberShake to improve their own national seismic hazard maps. And a suite of what we call empirical models for ground motions are now also informed by simulations we produce. So what are the ingredients we need to generate those ground motion simulations? We need to start with a source definition or an earthquake rupture forecast that includes the fault geometry, the different magnitudes you can expect on a fault, and the rate of earthquakes on those faults. That's important. We need three-dimensional models of the structure. So we will do tomography using data to invert the geology and it's more the velocity structure through which the waves will propagate. We do that using other supercomputers. We divide our work, and then we can use that as input, for example, for Blue Waters runs. Then we calculate the wave propagation and the attenuation, and we can then do also nonlinearity in the near surface and so on. So those are the three main things: the source, the wave propagation, and the source, the model through which it propagates the waves, and the wave propagation. So I'm going to talk about three groups, different groups. It's a subset of the people who are working on Blue Waters who have done improvements in the last year to their models. One here is on the source improvement from the Graves and Pitarka model. So Graves and Pitarka has a full system for creating ruptures, doing the wave propagation, and site response, and all that. I'm focusing here only on the rupture generator. What you see here is the plan view of, imagine a fault that's vertical fault here, and you would have a hypocenter somewhere around here, and this shows the slip displacement, a snapshot, and how much slip you expect on that fault from there. The rise time here, again, just shows you how fast this slip is happening on that fault, and the rake shows you the vector of those displacement and the slip and so on. So they have various models to come up with that. This specific Graves and Pitarka model is based on full dynamic ruptures. So when you prescribe a stress field and a real fault, and then you let the dynamics produce results, they ran thousands of those, developed statistics, and they come up with this simplified model that's fast to run, that can be used for a lot of simulations. So they've worked to improve their model and to incorporate features that would better allow a better fit of data as they go to high frequencies. So I'm focusing here on only one thing, is the correlation of the slip, the rupture speed, and the rise time, as they made changes from 2010 to last year. So here we have, again, just showing the fault plane here. The hypocenter is in this green star. And you look at these, this is a 2010 version and the 15.4 version. Well, it's hard to see if there's anything really different. Do we expect big differences? Well, actually, the refinements are really subtle to the naked eye, but they lead to significant differences in ground motions. So let's look at that. So at the low frequencies here, what these plots show is the distance and some measure of the ground motion intensity on the y-axis. The details are not really important. The different lines here show empirical models that have been calibrated with a lot of data around the world, and their median and standard deviations is shown there just as a reference. So you can see that for these low frequencies, this is about 0.3 hertz. The models, the model hasn't changed much as we went to 15.4. But when you compare at higher frequencies now, we're at 3.3 hertz, you can see that the original GP 2010 had much higher ground motions here than we get here, and this is not consistent with the average of the empirical observations. So these subtle differences you saw in breaking the coherence of the wavefront as it propagates through the fault really help us get better results at higher frequencies. So this was calibrated, all done through Blue Waters. And this was tested against various sets of data as well, validated. Another team here, that's Roten and Olsen et al. You've seen a little bit about that when Phil, my colleague, presented the paid program yesterday. But we're including now plasticity in the near fault material. So if this is the fault trace here, allowing to have plasticity that's based on this Drucker-Prager model was done. And this is based on basically how fragile the rock or how broken up it is, and it changes the velocity and also the output in terms of ground motions. And I present this as well, so this is important to add this plasticity nonlinearity, but this code was optimized through the paid program for both GPU and CPU versions and performs extremely well. It's very impressive what they've done. So we need the paid program. So some results here. So on the top here, this is a 4 Hertz simulation of a magnitude 7.7 San Andreas simulation. And the only thing to notice here is that the red values are very large, so above 1G mostly. In terms of acceleration, this is a 2 Hertz simulation. When we add the plasticity, the ground motions go down. And once we compare with empirical models, again, the overall bias on this plot here on the right shows it's very large. Here, it's mostly around 0, so this is more consistent with what has been observed globally. So this is a good improvement doing that. Another group, so that's a group with Riano, Bielak, Taborda et al. They're looking at effects of topography on ground motions. This, again, was all run on Blue Waters. They started using, this study is done with Hercules. So far I've talked about if we just talk about wave propagation, we have the Graves and Pitarka code, we have the AWP from the previous team, we have Hercules. One thing we try to do is not just to marry one code. We want to have the diversity of the different epistemic uncertainty in there. It's very important for us to support multiple codes to solve similar problems and try to see what are the advantages both numerically and in terms of physics. So that's why I picked those 3 examples, 3 different codes. This is Hercules, this is a finite element code, and it uses E3 structure for the meshing, which allows to increase the resolution as you go, say, modeling a hill. So what they've done, they have this, and then they convert the cube to tetrahedra particles, partitions near the boundary elements. And what they've done, so they ran this suite of synthetic mountains with different aspect ratios, different heights and so on, different length to bandwidth ratios and all that. And they ran systematic simulations using a point source earthquake, assuming that. And they came up with normalized results here. This is just to show you kind of things that they can see on having the source affecting the mountain will change how much amplification you get. These plots are just showing the amplification versus a flat model where you don't have topography. And then they can define the frequency dependence based on the hill and so on. And we know, as you can imagine, the waves that are trapped and the frequency of those waves have to be commensurate with the scale. Well, they've done that in detail here because there's not a lot of data on this. And they found that the different amplifications of course, are important, and depending where the source is relative to that mountain. So then they took that and applied it to a real case. So we have here a region near, just north of Los Angeles. Here's a cross-section of the area. There's an earthquake here, and then what they did is they simulated that. Here you have a velocity profile, so it shows very stiff sites, and this is a topography shown here. And the specific metrics are shown below are not that important, just to show that the blue line is if you consider that the land is flat and you don't have topography. The red line shows that you have a lot of variation that are affected by this topography, and it's not negligible for some measures, and definitely you have a lot more variation in ground motions than you would expect if it was a flat land. So that's an important conclusion. So we've talked now about pushing the ground motions to higher frequencies, and some of the physics we include. This is not exhaustive, it's just to highlight a few of our teams working on different aspects of the problem. But now I'm going to move on to another tool that is made famous through Blue Water's allocations, and it's called CyberShake. CyberShake is doing what we call a probabilistic seismic hazard analysis. It's when you integrate over all the different sources, all the different wave propagations at a site, and then you come up with a probabilistic hazard curve of exceedance of ground motion at your site for a given probability. So this is what is used mostly by engineers. And what we're doing here is a fully physics-based way of doing that instead of using empirical models. So again, the same ingredients we described before. We have an earthquake rupture forecast, so where the faults are, the rates of earthquakes, and the magnitude distribution. We have a kinematic source model. This is actually using the Graves and Pitarca one. So these faults here, by the way, for a given region, we're going to simulate like 40,000 earthquakes. So that's a lot of earthquakes we simulate there. Then we use a 3D velocity structure that will the waves will propagate through, and a wave propagation code, in this case AWP, which was also optimized through the paid program. From that, we obtain seismograms and what we call intensity measures that are used by engineers at each of the sites for each of the rupture that was computed. We get those hazard curves that most of you are familiar with in different domains. We can disaggregate to see which controls the hazard, which sources, magnitude, distance, and so on control the hazard. That's really useful for engineers when selecting ground motions for their own building simulations. And from that, we can compute maps. So this is the map of the Southern California CyberShake study. We've done numerous versions of those. The last one was 15.4 on Blue Waters. So now we're extending. So the black box here shows what we've done before with CyberShake in Southern California. We're moving now to Central California. So in the last almost 7-8 years, we've been working in SoCal. We know, how to set up the jobs and so on. Moving to a new region posed a lot of scientific questions and also computational issues, and we did a lot of calibration and so on. So this new region that we just finished at the end of March is shown in magenta here. We're moving up to Central California. It's twice the size of the original CyberShake map. We have selected the grid points at which we compute hazard curves, so all those 40,000 or so simulations of earthquakes are propagated to these 438 sites. We started by picking recording stations from the seismic network and so on, water pumping sites and so on, and then we filled it up with a grid so we can generate the map at a 10-kilometer spacing. And so now how we use Blue Waters for this, we computed two different velocity structures, one 3D and one 1D. This is a 1 Hz simulations, it's linear at this point. We used Titan and Blue Waters together for the first time. We averaged about 1,300 nodes, CPU and GPU in 31 days, maximum of 5,300. So we use close to 1 million node hours. So we convert back to cores because Titan has a different count. It's close to 22 million core hours on this. We use workflow tools from, so Pegasus, HD Condor, and Globus were used. And they were able to dispatch about 16,000 jobs for both systems. We transferred 300 terabytes of data because some computations were done in different places and so on. And with that, we generated 285 million two-component seismograms that we can retrieve and use as simulations, and 43 billion intensity measures are used by engineers and so on. The workflow tools managed more than 700 terabytes of data, so that's a lot flowing of data and information there. So this was made possible with reservations on Blue Waters, and we really appreciate that. So now we have a bigger map, Southern California and Central California. And my timer says it's over, and it's time to go back to my conclusions, right there. So there was tremendous scientific and societal impacts from Blue Waters allocation. So we have better understanding of data fits by including better physics. We developed CyberShake for PSHA, and the extensive validation we're doing is really allowing us to now have an impact on the engineering community. Thank you.